Module 1, Video 4, the inverse Laplace transform. In this video, we'll review the previous two videos, we'll discuss the uniqueness of the Laplace transform, we'll introduce the inverse Laplace transform, we'll explore the properties of the Laplace transform of sums of exponentials, we'll look at the partial fraction expansion of proper rational functions, we'll summarize what we did, and we'll look forward to the next video. Review of previous videos. In the previous videos, we introduced the Laplace transform, which was the area under the product of a function of time and e to the minus st between 0 and infinity. We developed some properties of the Laplace transform, and we found some Laplace transforms both by using the definition and by using Laplace transform properties. Among the properties we developed were linearity, the multiply by e to the minus at property, the delay property, differentiation, integration, and the multiply by t property. We found Laplace transforms for the constant waveform, decaying exponential, the complex exponential, a ramp, a parabola, cosine, sine, a cosine with an exponential envelope, and the rectangular pulse waveform. There were a number of takeaway messages from the first set of transforms and properties, including the correspondence between an exponential rate of decay or growth and the location of the Laplace transform pole, how the poles of the summed waveforms were the poles of the components, how adding waveforms together sometimes introduced zeros into the Laplace transform, how delaying a waveform introduced powers of e to the minus s, how differentiating introduced a zero at s equals 0, how integrating introduced a pole at s equals 0, how multiplying by t introduced another pole at the location of the existing poles, and how a pole and zero at the same location can sometimes cancel each other out. Uniqueness of the Laplace transform. Given the definition of the Laplace transform, how do we know that a waveform is the only one with a certain Laplace transform? It turns out that the uniqueness of the Laplace transform can be proven, although that is a proof more interesting to mathematicians than it is to engineers. The idea is to prove that if the Laplace transform of a piecewise continuous waveform is 0, then the waveform itself had to be 0. That being shown, the uniqueness of the Laplace transform follows from linearity. If the difference between two Laplace transforms is 0, then so too must the difference be between the waveforms from which those Laplace transforms came. If we know the f of t for t greater than or equal to 0 that yielded a particular Laplace transform, given the Laplace transform, we know the waveform for t greater than or equal to 0. Remember, that doesn't tell us anything about the waveform for t less than 0, since there's no information about f of t for t less than 0 in our Laplace transform. It also doesn't preclude two waveforms differing at what are called isolated points. What are these isolated points? Consider two waveforms that differ only at a single point. That single point is called an isolated point. In the example to the left, the waveform is sine 2 pi t everywhere except at t equals 1, where the waveform has been assigned the value of 2. This is perfectly fine as far as the definition of a function goes. The function assigns a value in its range to every point in the domain. Isolated points, though, have no impact under integration. They have 0 width, so they can't contribute to the area under the curve. Even if two functions differ at isolated points, they will have the same Laplace transform. Isolated points are fine as a mathematical concept for functions go, but we would never use a function with isolated points to model physical reality where things tend to be truly continuous. There are very brief waveforms that do have an impact called wave impulses, and we will include those in our suite of waveforms in the near future, but impulses have finite area, not zero area, and can impact how circuits behave. Isolated points have no area and can't change how circuits behave. For our intents and purposes, the Laplace transform is unique. Inverse Laplace transform. Ignoring isolated points, how do we go about finding the waveform for a given Laplace transform? Formally, we can use the definition of the inverse Laplace transform, which says that f of t is 1 over 2 pi j times the integral of the Laplace transform times e to the plus st along a closed contour C in the region of convergence of cap f of s. The inverse Laplace transform builds f of t as a weighted sum of e to the st exponentials, which is the source of much of its utility in solving differential equation problems. The concepts and mechanics of the inverse Laplace transform as a complex contour integral are well beyond the scope of our circuits class and belong to the study of complex functions. We will take advantage of the uniqueness of Laplace transforms to do inverse Laplace transforms. We will develop ways to write the Laplace transforms of signals of interest where we can recognize the inverse Laplace transform. For Laplace transforms that are rational functions of S, that will be through the use of partial fractions. Laplace transform of sums of exponentials. Before we see how to use partial fractions to find inverse Laplace transforms, let's explore how the Laplace transform of sums of exponentials behaves. In this example, we find the Laplace transform of 2e to the minus t minus e to the minus 2t when t is greater than or equal to 0. This is a fairly typical waveform produced by an overdamped second-order system where there's some finite initial condition, but the first derivative is 0. By linearity, we can find the Laplace transform of each exponential component, and we see that the pole associated with each waveform is maintained into the waveform of the Laplace transform of the sum. We then put everything over a common denominator and simplify. The pole zero diagram for this waveform's Laplace transform shows the two poles at s equals minus 1 and s equals minus 2, as well as the 1, 0 at s equals 3. The numerator has a lower order than the denominator. Let's see if that holds up for a sum of a larger number of exponentials. Consider the general case of n exponentials with distinct rates. The rate of the ith exponential is p sub I, its pole location, and the weight of the ith exponential is k sub I. The condition here is that none of the rates are the same, so none of the poles have the same location. We proceed as before, transforming term by term, putting everything over a common denominator. In the numerator, each weight ends up scaling a different polynomial of order n minus 1. So the numerator sums to a polynomial of order n minus 1. Since the weights can be chosen such that the coefficient of the highest power vanishes or such that the coefficient of all the powers except the s equals 0 term vanishes, we can state that the order of the numerator is at most n minus 1. The denominator will always be nth order. Since the order of the numerator might vary, we can write this rational function in a more general form where the denominator is nth order and the numerator is mth order. For our sum of exponential waveforms, the order of the numerator is guaranteed to be less than the order of the numerator. The order of the numerator is guaranteed to be less than the order of the denominator. We say that the Laplace transform of a sum of n exponentials is a proper rational function, where proper means that the order of the numerator is strictly less than the order of the denominator. Partial fraction expansion of proper rational functions. Let's work backwards to the time domain from a Laplace transform that's a proper rational function. Again, a proper rational function has a numerator, here designated b of s, whose order is strictly less than the order of the denominator, here a of s, generalized to recognize that the Laplace transform could be written such that the highest power in the denominator has a coefficient that's not 1. Let's start with the case that all the roots of the denominator, the pole locations, are distinct and real valued. If that's the case, we know that there are n coefficients, the weights of the exponentials in the waveforms. A proper rational function written in this form is called a partial fraction expansion. Each weight is called the residue of cap f of s at the pole location. As with the inverse function, there are methods from complex variables to find the residue at each pole, but we will use a more mundane approach that leads to the same results. That approach is called the cover-up method. The cover-up method. First, we factor f of s into poles and zeros. We don't actually have to factor the numerator, but we absolutely have to ensure that the coefficient of the highest power of the denominator is 1. For f of s so written, the scale factor k will be the ratio of the coefficient of the leading power of the numerator to the leading power of the denominator. We can see the poles, we can see the zeros. There's n poles and there's m zeros. We then equate f of s written in partial fraction form to f of s written in factored form. Let's say we're interested in finding k sub 1, the coefficient of the pole at p1. We multiply all sides of our f of s equals partial fraction form equals rational factored form by the term s minus p sub 1. That leaves k sub 1 in the first, as the first term in the sum and takes s minus p sub 1 out of the denominator. In practice, we cover up the s minus p sub 1 term in the factored form. That's why we get the name cover-up method. Next, we evaluate what's left at s equals p1, the pole location. When we evaluate the partial fraction sum, all the other terms except for k1 go to 0. And when we plug p1 in for s and what's left of the factored form, we get the value of k1. We do this again for k2 up to k sub n, covering up and evaluating the pole values. To find k2, we cover up s minus p sub 2 in the factored form, and then we evaluate what's left to find k2. We do this repeatedly until we found the residue for each pole. Let's go through an example of using cover-up where we can see how some of the details of doing this in practice work out. It's not as bad as it seems in the derivation. First, here's the f of s we developed earlier. As soon as we factor to the denominator, we know that we can write f of t of the form k1 something times e to the minus 2t plus something times e to the minus t. When we write f of s in factored forms, we put it equal to partial fractions. We equate the factored form with the partial fraction form. We don't have to put the weights k1 and k2 over the s plus 1 and s plus 2 terms, just leave space for the values that are going to go there. We read this as something over s plus 1 plus something over s plus 2. To find the something, the weight of the s plus 1 term, the residue of f of s at s equals minus 1, we cover up s plus 1 in the denominator of the factored form, and we evaluate what's left at s equals minus 1. Here we cover up s plus 1 in the denominator, and then we evaluate what's left at s equals minus 1, and the result is 2. You put that back in over s plus 1, and then you do the next term. To find the weight of the pole at s equals minus 2, we cover up the s plus 2 term in the factored form, and evaluate what's left at s equals minus 2. Here we find that value is minus 1. You put that back in, and now you're almost ready to inverse transform. It's best practice when doing partial fractions to partially recombine the expressions as a check. Were we to put everything over a common denominator, the coefficient of the highest power of s in the numerator has to be the same as in the original f of s. Since 2 minus 1 is 1, we have the correct coefficient of s, and we trust our partial fractions. After the check is done, then and only then should you inverse transform term by term to recover f of t equals 2e to the minus t minus e to the minus 2t for t greater than or equal to 0. As always, we learn nothing about f of t for t less than 0. That information has to come from somewhere else. In summary, in this video, we saw that for the kinds of waveforms we are interested in, the Laplace transform is unique. We don't have to worry about isolated points or other matters of interest to mathematicians, or even the formal definition of the inverse Laplace transform as a contour integral in the complex plane. We saw that when the Laplace transform of a waveform had distinct real-valued poles, we could write the Laplace transform as partial fractions, a sum of first-order terms. We could find the weight of each term, the residue of the Laplace transform at the pole locations, using the cover-up method. Then we could inverse transform each term individually to recover a sum of exponential waveforms. In the next video, there are still 4 cases to deal with, special cases. What to do when the poles are complex valued, they come in complex conjugate pairs. What to do when there are repeated poles, higher order poles. What to do with any powers of e to the minus s that show up. And what to do when f of s is a rational function, but the numerator order is as big or bigger than the denominator order. We'll deal with these cases in the next video. This has been video 4 of Module 1 in EE300 for fall 2016. This is the inverse Laplace transform.